Okay, in OC, we can execute the DE stop deploy at this time.
Copy. Execute.
And you're going to continue.
Copy, go.
And I can confirm the motor stopped, and we're going to continue with 66.011. And that command line looks good. You're going to execute.
Execute.
And you're going to continue.
Copy. Go to continue.
Stand by for review.
Standing by.
And OC, you're going to move the minus J2 mid-boom motor.
Copy. Go for move.
And the motor status is moving. Oh, and OC, you can queue up the stop command in step 12.
Roger.
Project Science, this is Mom on Ops. Report to the flight control room, please.
Project Science, welcome.
lead on ops. I can confirm the minus J2 latch event for layer 5.
And OC, this is DevOps on Ops. You are go to execute the DE stop deploy.
Executing.
And you're going to continue.
Copy, go.
Okay, and I can confirm that the motor move is stopped. We're ready to continue with 626.013. DU to operate frame 0. Command line looks good. You're going to execute.
Execute.
And you're going to continue.
Copy, go.
Okay, I can confirm operations frame 0. And at step 626.014, Duck Lead has confirmed the team is ready to continue. And we're ready for 66.015. The command line looks good. You're going to execute.
Hitting.
And you're going to continue.
Copy, go to continue.
And stand by while we review motor move parameters.
Standing by.
And OC, you are going to move the forward MTS motor pair.
Copy, go for move.
And the motor status is moving. And OC, you can queue up the stop command.
Roger.
I'm here.
Hello, you are watching a live commissioning of the James Webb Space Telescope. Today we have the exciting news to bring you that we are looking to finish the unfolding and tensioning of the heat shield. And right now they are working on the final layer, the fifth layer of the heat shield. And I'm Michelle Thaler. I'm an astronomer at Goddard Space Flight Center. And I'm working from my home today because of the COVID pandemic. So I ask that you all give us some patience with this broadcast. We want to make sure that people have a chance to see live this wonderful and historic event. And I'm joined by Keith Parrish. Keith is actually right now live at the Space Telescope Science Institute at the Johns Hopkins University in Baltimore. And above us, you can see live footage of the MOC, or the Mission Operations Center. And this is where people are working on the heat shield right now. So, Keith, we took a brief pause in our commentary. Could you bring us up to date? What is going on right now with the James Webb Space Telescope?
Yeah, so we took a short pause. We're currently all of our data coming down from Webb is coming through our Canberra ground station on Australia. So shout out to our Canberra folks down there. We're currently in communication with them. We'll be in there for another couple hours until we hand over to our Madrid station in Spain. So we took a little pause. We always want to make sure we're good to go before we go into the next operation. So it took a little pause to make sure all of our communication with Canberra was solid, and it is. So we just resumed layer 5 tensioning, and we actually have done we have 6 corners to tension. And we've tensioned the first 2. We are actually currently tensioning what we call the 4, the 4 side, which you can see up on what we call our observatory visualization tool right there. And you can see just a little bit of separation up there at the top as that layer spreads on that corner.
And once again, for those people that are just joining us, the graphic that you're seeing to the left of your screen is actually correct in real time as to what Webb is doing right now, and that's based on data and telemetry coming down from the telescope. Is that correct, Keith?
Yeah, that's right. So all that information is coming down from Webb right now. Our team that created this, what we call the OVT, that's our acronym for it. It takes all that data and it creates this visualization of what's going on Webb, and it really kind of gives us a connection to Webb, and is what it's doing. We know this isn't a live shot of Webb, but it really does give us sort of that spatial awareness that the engineers need. Again, it's really about the data, the ones and the zeros, and all the telemetry that's coming down, and we have thousands and thousands of data points coming down. So we take all that data and we make these images to tell us exactly what physical configuration that Webb is in right now. And you can see you can kind of see as you go down to the I do have my model here. I don't know if I can throw it. So what we are doing right now is we're tensioning up on this side right here. You can kind of see a little bit this front corner here. We've already done the fifth
Keith,
layer.
Just a note to the directors of the broadcast. Could we get a picture of Keith?
Oh, I'm sorry. I'm pointing to something you can't see.
Can we get Keith back on camera? Thank you. There you go.
There we go.
There you are.
I'm big too. Okay. So this is a model of and I got to get it right here. So we're actually tensioning up right now. You can see on the OVT when I'm not on the camera, you can see this is what we call our forward part of our sun shield, and we're tensioning layer 5 right there. If you swing around this way, we've already done these 2. We've already done this side, and we've already done this side. So right now we're on 4, and then we'll eventually do our aft. This is our aft side. We'll do that, and right after we finish our 4. So yeah, we're running out of cables to wind up. We started out yesterday moving 90 cables. And right now we're down to our last 18 cables. So the team has been winding those up and that's what actually creates that tension on the sun shield.
We've gotten some questions from social media, and remember that you can use the hashtag #AskNASA if you'd like to ask some questions live. And there's a couple actually that talk about the shape of the sun shield. So there's why was this shape determined? This person says, why wasn't it oval shaped or circular? Can you give us a sense about the design of the sun shield and why it looks the way it does?
Yeah, the sun shield is actually shaped. Basically, it's no bigger than it has to be. Any larger than it is, and that would have been even more engineering challenges. So we have requirements on how much sky that the telescope can see at each time, and then the shape of the telescope, the shape of the sun shield, lets us pretty much observe 60% of the sky at any time. So we can pitch forward with respect to the sun and still keep our secondary mirror in shadow. We can pitch back quite a way, well over 50 degrees, and still keep our telescope in shadow. So we can kind of tilt the telescope back and forth quite a bit, front and back. Now on the sides, we only roll about 5 degrees each way to the side. So that's why the sun shield has this sort of narrow shape on the sides. It's 50 some feet on the sides, and it's 70 some feet long on the length. And then instead of making it a square or a rectangle, we don't need it to do that. So we tried to limit as much material as we had to handle on orbit. So that's what gives it this sort of iconic kite shape, is that it didn't need to be anything other than a kite to provide that provide our telescope with that view of the sky at all times.
And I should just say as a shout out, that was Andra on Twitter that asked that question. And then as we see, there's a graphic up here about just how much temper differential there is between the hot side and the cold side of the heat shield. One of our social media guests asked, does the observatory itself, does the mirror itself pan around a lot to look at the sky?
On ops, another deployment status update. I can confirm the latch event on the forward MTS pair for layer 5.
Okay.
All right, good news, Dep Lead. Thank you. Good news.
Okay, so what you just heard there, you just heard our Dep Lead, Hillary. She just told us that we are finished with the forward. So we've done 4 of our 6 corners.
And OC, you are go to execute.
Spin that image around to the backside, and we got 1 to go. So we're really getting down to the finish line now. So back to your question. Or back to the question, we maneuver the whole observatory. The whole observatory maneuvers to look at whatever it's imaging, whether it be a galaxy or other object. There was early studies that actually moved the telescope relative to the sun shield, and that's a really complicated thing.
So operate frame 10. Command line looks good. You're go to execute.
Executing.
You'll hear us being interrupted by live updates from the MOC, the Mission Operations Center. So don't worry if we're pausing. We're listening to what they're saying.
Yeah, exactly right. So that's our Dep Ops engineer, Nancy. She's communicating again with our flight controllers in the room to communicate what commands that our deployments team want to send up to Webb. So again, we just maneuver the whole observatory. It's just better to maneuver it, make it nice and rigid and solid on orbit, and just maneuver that versus trying to maneuver the telescope individually.
And I can confirm
that's what really drove that sun shield shape and size.
66.018. I have confirmed that Dep Lead and the team are ready to continue. So we can go to 626.019. And that command line looks good. You're good to execute.
Executing.
Are you starting to get excited, Keith?
Yeah, well, that was the command. We're actually sending a command to start turning those motors.
Happy go.
So let's talk a bit about the importance of the sun shield, and there are many different aspects of that. This really is an exciting piece of technology, and this is something that for a space observatory like this we've never tried before. Can you give us sort of a pan back, sort of the 30,000-foot look at why this sun shield is so incredible?
And OC, you're going to move the aft MTS motor pair.
Copy.
There we go. So. I do like to let people hear the commanding there because it's really, it's interesting.
Roger.
There's there's more than just one command that goes up. Our flight controllers and our DepOps lead they're checking everything that's coming back and making sure that the next command is the right command. So they're double checking and double checking. So that's a lot of the back and forth you hear there. But as you can see on the graphic there, you'll see our motor counts.
Motor pair status has changed to moving.
Yep, there we go. So you'll start seeing those counts. That's what we call a field director, which keeps track of our motor position, and you'll see those counts starting to increase as that layer and separated and those cables are wound in. So I think the big, back to your question, the big challenge with this type of deployment is we're doing 5 layers. We have to handle 5 layers, and everything. We're pretty good at deploying things that are rigid, but the membranes are rather they're floppy and they want to float around. We have cables that we don't want to get slack, so we're really trying to do an intricate operation right now, 560 some thousand miles away from the Earth, and control every aspect of the position of these layers. And I think that's really where the challenge has been, is to make sure that we understand every second of the deployment where these layers are. So there's a lot of features built in that aren't really apparent in any of the things that you're seeing right now that keep these layers very controlled and make sure that they're not floating places that we don't want them to be. And that's really been the really one of the challenges for such a large sort of floppy deployable item that this sunshield is.
Speaking of it being kind of large and floppy, we've gotten several questions on social media. So Shivani from our YouTube feed asks, what happens if even one of the sunshields get damaged? And there are other ones about micrometeorites. So, tiny little bits of rock flying around in space. Well, how resilient is this heat shield to something like that?
Oh, it's everything from the materials sort of its raw materials that was chosen for its strength. To be able to handle the environment of space, what it's coated with to make these really sort of colors is coated. Is everything has been designed. It's got lots of reinforcements. You can see in some of these this video of the real shield now. You can see a lot of seams. I do want to give a shout out to our membrane. We had a vendor that created these membranes and had to stitch them all together, so to speak. And it's completely reinforced so that if we do get tears, they won't propagate. And as far as micrometeoroids, we do expect to be hit with micrometeoroids. The good thing is that they're not very big and they won't do much damage. So we actually, one of our early developments for this material is we actually took it and hit it with high velocity projectiles moving several kilometers per second to make sure that the material could withstand that. So over the lifetime, we do expect really, really tiny microscopic holes to develop, but again, that's all accounted for in design. So it's rather rugged. Once it's all tensioned up, it'll be fine.
And you were talking about the fact that this is this sort of large, huge sail that we're unfolding little bit by little bit in space. And of course, while there isn't any air or atmosphere where Webb is, there is something called the solar wind. And the solar wind is actually a wind of high energy particles that are coming off from the sun. So not a wind in the way we think of it, but a wind of actually high energy particles. Does the solar wind have any effect on the heat shield and its pointing?
Oh yeah, so we get something called solar pressure. And again, if the whole concept of solar sails, to possibly travel around our solar system, with free propulsion from the sun. It's a very small force, very, very tiny. It's not like the wind blowing, but it is a force. It's a physical force. The sun, the solar pressure that hits the sun shield. So we have to account for that. It will try to move us around. The biggest thing that it does to us is it's offset. So what I mean by that is the solar pressure will tend to try to turn us, and we counter that turning force with some reaction wheels in the spacecraft. And then ultimately, those wheels get spinning so fast we have to fire our onboard propulsion system to unload them. And that takes fuel to do. So I think earlier in the week, we deployed something called our aft flap. off the back of the sunshield main structure, and that aft flap is intended to sort of a sailing analogy, sort of to counter, almost like a little bit of a rudder to help us counter some of those forces, and ultimately that leads us to using less fuel on orbit.
And is that's something that is a limitation to some degree for this observatory. It does have a finite amount of fuel to do that. Is that correct? That'll be one of the lifetime limitations?
That's right. So fuel is our only known limiting life item on board. So obviously we wanted to take a lot of it, and we worst cased everything, and then we said, hey, once we worst case all of our conditions, meaning we don't get a very good injection from our Ariane 5 vehicle. We do all of our burns late. They're not very efficient. We have lots of momentum that we have to unload, lots of solar pressure. If all those things go bad, we still want 10 years of fuel. And so all of our worst case calculations is how we came up with how many kilograms of fuel to take on board. Fortunately, so far, those worst case conditions, I think as Amy said yesterday, we conservative. So all those conditions so far have not been on the worst case. Our execution of that first burn, and again, everything has been really, really good. So we expect to use significantly less, and we expect to have much more than the 10 years.
And I'll just mention that the question about the solar sail effect on the heat shield comes from Alan on Facebook. So thank you very much for your question. There's a question coming in that maybe I could take a bit of a crack at answering myself. And Keith, certainly you can chime in on this. But Mike on Facebook asks, who will be able to use Webb? Just NASA. And I think this is a chance to kind of talk a bit about the international nature of this mission. Mm-hmm. So absolutely, it will not be just NASA that is using the Webb Space Telescope. The Webb Space Telescope has several major international partners. Our big partners are the European Space Agency and the Canadian Space Agency. And so there is a time allocation to the major partners in this mission so the European astronomers, people working with the European Space Agency, and also the Canadian Space Agency. However, like Hubble, the Webb Telescope is a world observatory. And what will happen in the future is that there will be committees of astronomers that every year will review proposals from all over the world, from teams of scientists who want to use the Webb Telescope for their own research. And again, while the main organizations responsible for the operation and the building and testing of Webb will have some time allocated to them automatically, a lot of this will be open to the public in the sense that professional astronomers from all around the world will be able to use it. And it's not just the observations themselves. The other thing that's really, really important to talk about is the archive. That the data taken by the Webb telescope, when you're an astronomer, say, I actually have been honored to use the Hubble Space Telescope myself in the past. You write a proposal to this committee of scientists every year that then ranks the proposals in terms of their priority, their science priority. And then you get your data, based on whether you make that priority list. And if you don't, you can apply again next time and all of that. But that all goes into an archive. And that archive, after a certain amount of time, is public, and anybody can use the data. So if you're a scientist that's won the proposal, you should get a first chance to look at your data and make your discoveries and observations that you want to. But then eventually that data gets put into an archive where anybody can use the data. So this is a world treasure. It's not just NASA that will be using this observatory, and it's not just NASA that built the observatory and launched the observatory. This has been an international program from the very beginning. So that's something we're very proud of. Let's see. So I know, I'm getting, more and more excited. The heat shield was a tremendously complex part of this observatory. So for people that are just joining us, maybe you could give us some sense, Mike, a little bit about the number of actuators, maybe talk about what an actuator is and the number of things that had to happen to get this thing to unfold into tension. It's something that, all of us are just, thrilled to see happening so beautifully in front of us. Can you give us a sense of that? Yeah.
So, one of the big things that, as we've talked about is the amount of mechanisms that we use, specifically the pin. So when we fold up all these layers, we have to sort of secure them to the primary structure, which we deployed back on day 3 after we launched. So those pins, there was 107 of them. And we had to sort of spear all the material, put holes in the material, and actually push them through to connect to our structure. Here you're seeing our solar array come out in this graphic. Again, we were able to capture that live on launch day, and that's that antenna that's currently communicating with Canberra. So here's these forward structures. All of the material that's now out, was pinned to this structure, meaning it was actually there was 107 pins that went through it and actually held it down to that structure. And we had to release all 107 of those pins, and we did that over the last few days. And then we had this cover roll up. This cover rolls up as we release those pins. You can see the aft going there, and on the front you can see our cover rolling up as we release these pins. Now this was our big event on New Year's Eve when we released the final set of pins and the covers unrolled, and we actually used these telescoping booms to pull out all 5 layers. So this was quite the big event for us as far as changing Webb's overall appearance. It made a dramatic change in our temperatures when we did these 2 booms. Again, you can see that cover rolling under right there. And this is our other side coming out. So I think releasing those 107 pins was quite an achievement. Again, because one doesn't release, then our membranes are trapped, and we would have had to go into a different contingency operation. So again, you're seeing what's going on right now. This is old footage of when we tested the sun shield on the ground for the very last time. So everything you're seeing in this video right now, in this time lapse, which is probably just a few seconds long, is taking us yesterday and today to do. So you can see in this time lapse, the last layer's tensioning up, and you can see what a dramatic change that it takes as it is stretched out like that.
And we have a question from Gray Squirrel on Twitter, and this is one that maybe I can take to give you a little bit of a break, Mike, but but you can jump right in. So Gray Squirrel on Twitter asks, why does it take until June to start science operations with the James Webb Space Telescope, and what else needs to happen after reaching L2? And I think this is a chance to give us a little bit of a look ahead about what's going to be going on after today and after the heat shield happens. So one of the things I can say is that a lot of this has to do with cooling the telescope down. This is an infrared telescope. The reason we have these incredible heat shields is so that the observatory itself can be very cold, very sensitive to the infrared radiation from space. And so the things that will be happening in the next few days, personally, I'm really looking forward to the deployment of the secondary mirror. There are these very large boom structures that will come out in front of Webb, and that will bring the focusing mirror. The primary mirror is that beautiful 18-segmented gold mirror that all of us have been talking about. But then there's also the secondary mirror that needs to come out on these booms that all of these 18 mirror segments will focus the light up to. And then that light will be actually reflected back down into the instrument package for Webb. And so that's one of the big deployments that will happen in the coming week. Just listening.
Exactly right. That's our next one that we're really, really excited about, because that's, again, the sun shield is great engineering. It's absolutely needed for this mission, and it's incredible. But the sun shield is there to cool what we really want, and that's that telescope and those science instruments. So we really want to get those deployed next.
And then after that, we have the full deployment of the primary mirror. So that 18 segment mirror has 2 wings. The wings will both be deployed. So you can see here in this animation, there's the secondary mirror that's coming out on this large boom. That's the focusing mirror. And you can see that it will be focusing things down to the sort of that black protrusion coming out of the center of the gold mirror. And then after that, the 2 wing segments will also be deployed. And once that happens, we will have the fully commissioned and huge
thing is it takes about 2 months for our telescope engineers and scientists to sort of align it and sort of focus it, so to speak, and to make it working at an operational as an actual telescope. And then it takes another couple months alongside of that, it takes another couple months for our instrument teams to get their instruments calibrated and get them all checked out. So it all adds up to about 6 months before we would actually get some of our first science. And that cool down drives a lot of what we call our entry criteria. Like we cannot let a the telescope can't do certain things until it reaches certain temperatures. So that cool down on top of these really, really precise operations that our instrument and our telescope teams need to do all kind of add up to that 6 month period or 4 months period on top of the, what we're doing right now in this first month, 1 2 months.
You've heard us say before just what a technological marvel the Webb telescope is. And talking about some of these deployment activities, these commission activities that are going on, Keith there mentioned the idea that the alignment of the mirrors needs to happen. And of course, we have 18 wonderful gold-coated segmented mirrors, but they all need to work as one continuous telescope mirror. And so part of this commissioning will be to actually do focusing of each of the 18 segments. Keith, maybe you give us a sense that the segments can all move independently. Is that correct?
That's right. They can tilt. They can move in a lot of different directions. And again, it's not a lot of movement, but they all can move in different directions to align themselves. They can also be pushed and pulled a little bit to sort of change their radius of curvature a tiny bit. So all those different movements have to be well coordinated, and it's quite the challenge that the optics team has coming up for them to do that. So that's really groundbreaking. Really groundbreaking what they're getting ready to go into, which is aligning those 18 segments. So they have full control over all of them. But even though they have full control over them, they have to get the data back down to the ground or where they are. And again, a lot of ground system processing to compute the next move, and then they'll just keep cycling through. And at the same time, they're imaging. They're taking reference stars to make and using those reference stars to help them align and focus the telescope. It's a very painstaking process. It's groundbreaking, but it's going to be really something when they get it all done.
And one of the other parts of the commissioning that I think is just incredible is that because this telescope is operating at just low temperatures, a lot of people are familiar with the idea that materials expand and contract and change shape as they change temperature. And so these mirror segments, which are made from beryllium, it's a type of metal that behaves very well under very cold circumstances. It keeps its shape, it works very well. The beryllium segments actually were ground to a curvature that isn't correct when it's at room temperature. They actually need to cool down to this operating temperature that we said, which is close to minus 400 degrees Fahrenheit. And it's only at that operating temperature that the curvature of the mirrors are correct. Is that right, Keith?
Yeah. And again, that you're going back, again, the development history is just doing that very operation. Mom, and making those mirrors. So we'll stand by. I
see something happening in the mock. People are getting excited.
Okay. Here we go.
Mom, I can confirm the final latch signature on the aft MTS, which indicates that all 5 layers of the sun shield are fully tensioned.
How exciting.
Significant milestone accomplished. Job well done, Sun Shield team. Job well done.
Yeah, so...
Thank you, Mom.
All stations, this is Mom on Ops. All stations, this is Mom on Ops. Stand by for PM.
Hey guys, I just want to congratulate.
This is Def Ops. You can go ahead and execute GE stop deploy.
Copy. Executing.
This is incredible to see. You're watching live footage of the mock, the Mission Operations Center. It looks like we are very close to declaring victory on the deployment of the Sun Shield.
Yeah,
and I can confirm motor stop. We'll stand by here.
Congratulate our team downstairs.
Whatever they want to
do. Many years in the making, right here. So not just for NASA, all of our industry partners. It's just an amazing achievement. So I just want to congratulate our Sun Shield team right now. What an achievement.
Okay. Hey, I just want to take a moment to congratulate everybody. This is a really big moment. We have a bunch of work to still do, but Sun Shield has been unbelievable after many years. Sorry about that. Since I don't normally talk, we bring the mic down. Anyway, so I said this is a really big moment. I just want to congratulate the entire team. We still got a lot of work to do, but getting the sun shield out and deployed is really, really big. You constantly reinforce what I tell everybody, that the JWST team is the best in NASA. There is, hands down, nobody better than what we have here. You guys should all take pride in all these accomplishments. One of the things I've told folks, and I've even put in emails, this is so unique what we do in this mission. We are going to be bonded forever by what we experienced, through not only just through operations and with the mission ops team, but over the last, all those who've worked on it over 20 plus years. And finally, I'll just tell you what I put on Facebook last night when I shared the story. I just said the JVS team kicks butt. I didn't use the word butt. I used another word, but I won't use that word here. Congratulations, everybody. Hooah! Hooah!
Absolutely awesome. So yeah, this is we'll let our celebrations continue. This is incredible. What an incredible week. But folks like me are looking ahead right now. I'm looking ahead deployment and can't wait to get that out. So but congratulations to our entire team. Just awesome. And just want to pass along some thanks to, everybody viewing this, everybody who's been rooting us on.
And all stations, this is my line ops. We're going to hold right here for just a moment. All stations, this is my line ops. Just hold right here for a second. Enjoy your moment, and then we'll pick up with that.
Just as you said, it's so wonderful to have all the people that are joining us around the world for this event. This is truly incredible. When I first saw the design of the James Webb Space Telescope and just the ambition of it and the size of it and the scale of it and this giant heat shield that needed to come out and so many things needed to work, it took my breath away. And I'm here. I'm actually getting goosebumps. I mean, this is a wonderful, wonderful time. How are you feeling, Keith?
Oh, yeah, it's just, like I said, half my mind is going, woohoo, and then the half of my mind's going, let's get that, we got to get that secondary mirror out. So that's just how my mind thinks. So, but that's good. But no, this is really good. I mean, and Webb is absolutely, hopefully everybody is becoming iconic a little bit. It is absolutely a beautiful spacecraft. We did not design it to be beautiful. We designed it to be functional. But as a fact of making it functional, it's absolutely a stunning spacecraft. I did get to spend a few minutes with it in the clean room before we shipped it down to launch, and I was just amazed at just how beautiful of a machine it is. So, and that machine is really a function of hand built by this team. So a salute to them.
Absolutely wonderful. So to confirm, Keith, we have final confirmation that the heat shield is entirely extended and tensioned.
All stations, this is Mom on Ops. We're gonna jump back into the cast chair and continue with the coolest thing in space. There is nothing cooler in space than JWST. That's a fact. So, OC, this is Mom on Ops.
OC on Ops.
I love that. The coolest thing in space. It will be soon.
As you can tell, even though we finished this up, we're going to move on to this evening's activities right off the bat. So we have some more 24-hour operation there, and we're constantly doing new things.
At 626.021, Dep Lead has confirmed that the membrane tensioning is complete. So at this time, we're ready to continue at 626.022, DEU to standby.
Copy that.
So what's going on?
Clock looks good.
What's going on now is our we're going to start shutting down or reconfiguring our electronics and turning off our motors, and basically tell our electronics that have been driving these deployments that their job is done. Thank you very much. You did your job, and now you get to move on to your next thing. So that's what they're doing right now. They're just basically shutting things down and getting configured for the next operation. So you may hear some of that.
Well, just many congratulations, Keith. This is just incredible.
Yep.
So
awesome.
You hear about the preparations. Sorry.
No,
I didn't mean to step on you there. You've heard about the preparations.
Oh, I'm sorry. I keep stepping on. I just want to thank you guys for putting these productions together, because it's just awesome to bring
standby mode around
this out there.
We're ready to continue with 626.023. And that clock looks good. You're go to continue or go to execute.
Executing.
Okay.
So as Keith just said, they're getting ready to do the next things that will happen, and please note that we will be bringing you live coverage of these other major deployments. So the next one I believe will be the secondary mirror, and
you're good to
I don't know
enable.
exactly the schedule of these yet. That depends on what the engineers decide to do, but we'll have updates with that.
And you're good for
and
reconfig.
then
Happy, go for
and then the
reconfig.
deployment of the full primary mirror as well. So
And you're
those
good to
things are
enable.
coming up later in the
Happy,
week.
go.
Just listening to what they're saying at the mock.
Mm-hmm.
So seeing as we have a little bit of a pause from the Mission Operations Center, I'm going to wrap this up now because I think this is a wonderful chance to say thank you so much for everybody. Keith Parrish, thank you so
that
much for
prot
joining us
completed
and for all of
successfully.
the
We're ready to
amazing
go with
explanations you've given us.
66.024.
And this is a historic day.
The
The
clock
first
looks
major phase of the commissioning, the deployment of the Sun Shield is complete and successful. And I'm very excited.
That's
So
right.
thank you so
Sun
much
Shield
for
team,
joining us.
And thank you, Sun Shield team, and go Webb, go.
Go Webb. Absolutely. Thank you for joining us. Please join us again later in the week. Goodbye.